be referenced. So, and also we have made some observations regarding the use of the types in terms of, at least in terms of implicit conversion, that when an integer is being used in the context of a double operator, or an integer is placed in the context of a Boolean, expected Boolean, then how does the compiler handle these types and convert them, or would be able to give us more errors? We will talk some bit more about the type expression later, but before that we take on to the next most important feature of a language, which is indexed variables, that is arrays. So arrays in expression. So arrays will have to be looked at again from two perspectives. One, when the array references happen in an expression, either as a value or as a reference, and we will also have to look at arrays in terms of what happens when you declare an array. How is the type of an array set? Okay, sorry, something happened. I don't know. Is it fine now, I see?
Yes, fine now.
Okay. So we will start with the recap of a simple example. Here A is an array of integer of 10 locations. B and I are two simple integer variables, and we have the most simple kind of assignment that I can have, that I'm indexing ith location of A, array A, and taking that value, assigning it to B. So what is AI? What is AI is A as a variable, or the starting address of an array will have a base address. And this base address is what will be set in terms of offset in the activation record, in the stack frame. Now, if I'm indexing the ith location of the array, then certainly I have to take a stride from this base. In stride will have to be in the size of int. For example, if the size of int is 4, then naturally A0 will be 4 bytes from the base. A1 would be 4 bytes from base plus 4, and so on. So that is, I mean, simplifying this expression is one of the major reasons why C moved from indexing arrays starting with 1, which was the Fortran style, to indexing arrays starting with 0, because this expression becomes very simple. So AI, the actual address of the indexed location AI, is A plus I times size of int. So this is what we'll have to put in the computation. So when we translate this, naturally taking I and knowing the type of the array element, which is int, we have to get the size of that. So this is the size of the array element, and multiply I by that size to get the actual offset from base, which is T1, I times 4. And then get the actual address of this array, of this indexed location AI, which is T1 bytes from the base address A. So it is in AT1 in the 3 address code. As you recall, in 3 address code, we are immediately referencing in terms of bytes. So it is AT1 is where you will get this variable. And that you take to T2, and then you assign T2 to B. And of course, later in optimization, this T2 will get eliminated. And this is the translation that we are looking for. So this is our target. So two things, we'll have to naturally look at the grammar for this and look at how to translate that using different. So let us look at this grammar, which is, I've simplified everything else in this grammar to focus only on. So I have a statement, which is a simple assignment statement to a variable, which on the right hand side has an expression. And it can also be another type of assignment statement where the left hand side is not a simple variable, but it is an indexed location. So that is, that indexed location is represented by this non-terminal A. So if you look at rule 6, you see that A actually expands to ID. So E is an index expression, like in the previous example we had I. So E here basically represents that. Then ID here on A produces ID bracket E. This ID is the array name ID, and this is the array reference that is being made. So here in rule 2, we have an example. We have the rule which let expressions being assigned to array. Then we have two simple rules, 3 and 4. They represent all other kinds of expressions. I have just summarized them all as if in terms of either having a simple identifier or having an addition. Addition is just like any binary operator you can take, because I do not want to make things complex. At that side, we have already seen the arithmetic expressions. Now, besides that, in rule 5, we say that the expression could also be an A. What is A? A is an array index. So it could also be ID. So A can occur on the left-hand side of the assignment in rule 2, or on the right-hand side of the assignment in rule 2 or rule 1. And A denotes an array. This is what will be sufficient to index one-dimensional arrays. Now we know arrays could be multidimensional, and C does not treat multidimensional arrays differently. It treats multidimensional arrays as arrays of lower dimensional arrays. So it is array of like that. So if I look at that recursion, so we will say that, for example, let us go down below here at the declaration of array A. You know all this. I'm just reiterating to make it clear in terms of how we got to the grammar, so that we can use it effectively. So we say this is array A to 3, which is a 2-dimensional array. So we can say that actually, if I consider this, then I have A as a array of 2 elements. And what are those 2 elements? Those elements themselves are arrays of 3 elements. So I have an array of, this is the innermost dimension where I have array of 3 elements. And then I make A by making an array of those 3 element arrays. So this is array, this is the basic recursion that we are building up. From right to left is the innermost index to the outermost index. And C follows a row major layout in the memory. So these will be, first the whole row A0 will be laid out as I'm showing in the memory here. So A0, 0, 0, 1, 0, 2. And then the whole of row A1 will be laid out. And in this context, we have a simple access and assignment. So what will happen in terms of this grammar? How will this assignment statement look like? Naturally, it starts with the rule 1. So I have IDB assigned this expression, which is the right-hand side expression, which is an addition of two expressions, where the left expression is just C. This part is E. And then the right expression, this is by rule 5, is an array reference, which is A1. And that is two-dimensional. So by rule 7, I have A1 expanding to A2 bracket 5 bracket closed. And then A2 again is expanded in terms of rule 6 here, because it is just two-dimensional, which is the actual array AI. So we have array AI here of J. So this is how the whole grammar in a parse tree will look like. I just note that I used a drawing tool to create this parse tree, where I cannot write the square bracket symbol because it's the control symbol in that tool. So I'm using opening bracket OB for this and closing bracket CB for the closing. So if this is the parse tree and if this is the expression, then what is the translation that we expect? We start here. So first we'll reduce at this part. Yeah, this naturally C will get reduced to E first, but that really does not change anything. That does not produce any output. It just sets E2.log to C.log, IDC.log. But then IDI gets reduced to E4, again sets the log. And then when this reduction happens, that is reduction by rule 6 happen, then I know that I am indexing the ith row of this two-dimensional. So my stride here is not of a single element, but that of a row. So I have to take the stride on I, which is the size of a full row, which is, I know by the innermost dimension. I mean, how I would know is what will come slowly. But this is what has to come in the translation, that the inner dimension is 3. So in terms of array AI or array A, the index on array A is in terms of elements, which are an one-dimensional array of 3 elements. So naturally, if int is of size 4, then each of these arrays rows will be of 12 size. So array, the index I will be having a stride of 12. So I will multiply I by 12, put it to a temporary variable T1, and that is the reduction that I have got. Then I have J going to E5, which is just setting the log, and then I have reduction by rule 7, where I already know that I am at the beginning of the ith row, because I have already done T1. So within that row now, I have to take the stride, which is of the inner dimension, which is of J, and this inner dimension element now is single element. So it is an integer. It's an int of size 4. So that offset would therefore be J times 4. So I compute that in T2. And therefore the whole offset of Aij would be, first start from the base address A, take a stride on I, which is T1, then take an offset from that point on J, which is T2. So if you add up these two offsets, you will get the total offset from base. So I add them up as T1 plus T2 and get the total offset T3. And then I access that array A at T3 and put it to a temporary. So these are the things that happen when this reduction has taken place. And then that T5, T4 is what gets set as the location point, which is by reduction by T5. And then rest of it follows like a simple arithmetic expression. So C was already there, so that gets added to T4, you get a T5, and finally a. So this is the translation that we are looking at. So therefore, what is important is the fact that the stride would be simple to calculate if I know what is the type of the element that I'm talking. So if I'm talking of Aij, then I'm talking of single elements where the element type is int. Whereas if I'm talking just of AI, then it's an array of one-dimensional arrays. So my element type is array of size 3. So my array is of size 3 of integer elements. So these types get different. And once I know that type, I will certainly know the size of that type and I'll be able to complete the string. So that's the simple observation that you have to make to create the attributes and go ahead with the translation. So this is just showing you in more detail in terms of this is more for your what we will actually get into translating. So we will take this expression and try to translate that. The thing that I have changed here from the previous example, if you go back, is instead of having a simple variable in the first component, I have put a one-dimensional array indexed variable. So I have one two-dimensional array, one simple variable, one-dimensional array, and then I have three index variable ijk. And this naturally, according to this grammar, is the parse tree that happens. So which I would like to use in the translation. So the kind of attributes that I put here, and it is try to little bit concentrate and understand these attributes, is a.log. That is location of an array is a temporary used for computing the offset for the array reference. And how is that done? That is done by ij times w. So what did we do? Let's go back. What did we do? Here, what did we do? So ij refers to the first index I here. That is I1 refers to first index I here. I2 refers to second index j here. W1 refers to the width of the first type of W2 refers to the width of the second type of element 4 here. So I will have to collect these product terms and put them together, and the variable in which I compute those is called the a.log. That is the temporary that I use. Then I need to know the different information about this array. Because I need to know the dimensions, I need to know what is the inner dimension, what is the next dimension, what is the next dimension, finally what is the outer dimension. So this information would be available in the symbol table. So a.array is a pointer to the symbol table entry for the array name. So because there's a lot of information, so instead of just putting a whole lot of different attributes to maintain them, just make a reference to the symbol table. So this symbol table entry will have base, which is where the array would start. That is the basic offset point. So we assume that that is the base, and the type of the array, because I need that to complete the string. The base address of the array will be mentioned as a.array.base, because a.array is a pointer to the symbol table record for this array A. So the base component of that is the base, which will be used to determine the actual L value of an array reference after all indexes have been complete. So you need to add this base. Then I use a.type, which is a type of the sub array generated by. So we have here, like we showed here, we have a sub array here, which is the array of 3 elements. Okay? So we will need to have the type of the sub array, and we can have multiples of that depending on the dimensionality of the array. For any type, we will use for any type t, whatever that type is. We will use t.width to give the width, and use type as attribute rather than width, because From type, we can know more about the array than just the weight. Because given the type, we can always find out what is the weight. And for any array type T, we say that T dot element gives the type of the element that it is. So if the array type is EI, then the element is a one-dimensional array. But for EIJ, it will be a so that is how the element type will change. So with that, now we write the production rules, write the action rules, semantic actions for translation. ID assigned E is straightforward, which is what we did earlier. You emit the assignment. If I have E assigned E, then the right-hand side is E dot log, which is simple. But what will be the left-hand side? Left-hand side has to be, the array has to start at the base and then have the offset. The base we said is A dot array dot base. So we do A dot array dot base. And A dot log is the offset that we have computed here by summing these terms. So this is the A dot, this is the array dot base indexed by A dot log is what is the left hand side. So this is the assignment we have made. Plus we have addition we have seen, reproducing ID we have seen, and all that we are doing here, which probably we did not do when we are directly handling the respective expression. We had not mentioned about the type, but here we are maintaining the type because I need that to analyze that. So when I do addition, naturally, we have already seen that addition can be done only for the same type of elements. So we say E dot type is E1 dot type. Similarly, for reproducing ID, E dot type is ID dot type. If I have an array reference on the right hand side expression, then we say that E produces A. So I need a new location for this expression. So I do a gen temp. What is the type of E? Is whatever is the type of the array. So A dot E dot type is A dot type. And then I will need to create the read of that location. So this is very similar to what we did in rule 2. So we will take the array base, A dot array dot base, and index it with A dot log, which is the opposite. So that will be assigned to E dot log for giving the a referential access to this array. Now we have the actual address offset computation. So A produces ID. So naturally, I need to know what is this A dot array, a symbol table entry, because based on that, I will do the rest of the computation. So A dot array is lookup of the symbol table with the array name ID. So I look that up. What is the type? Type we said is A dot array is the element. So A dot array is the entry. So A dot array dot type is the type of the array. So what is the type of the indexed element? A is on the left hand side of the production. So what is A? A is the indexed element. So it has been indexed already. So A dot type, the type of A here is actually A dot array dot type dot element. We said that any type dot element, any array type dot element to element. Now I need to start computing the offset. So for computing the offset, I need a location. I do a gen temp, and then I will put the actual ij times wj computation. So A dot log, the new location will be assigned E dot log, which is the index value, times I know the type is the A dot type. I know the element type. So I will have to get the width of the element type. So the element stride is in terms of the width of the element type. So I have got the element type in A dot type. So I will take the width of that type, multiply it by the index value, and I will get the offset for the IDE index. Now, if I have recurrence, then that will be done in the similar manner. what is the type of, what is the entry in the symbol table for A? It will be same as the entry of symbol table in the A1 on the right hand side. I do not need to do a lookup because I have already come to this through a reduction into A1. So already A1 dot array gives me the same pointer as the symbol table entry of this array. So I can just say A1 dot array to A dot array. A dot type again is the type of A1 and dereferenced by the element type because I'm making an index. So it is A1 dot type dot element. I need to compute the offset. So I generate a new location. I finally need the offset here. I mean, I need a separate temporary here because I already have an offset coming in terms of A1 dot log. And I will have an offset coming from, so I'm now in the inner of it. So I have to get, I already have an offset which I have got in A1. And further to that, I have to set an offset which is based on the index value. So in T, I will compute that the extra offset that I'm getting. So T is E dot log, which is the index value, times A dot type, the element type, dot width, exactly as we did in the rule 6. So this is exactly the same, except that on now I'm putting it in a different temporary. So I got the additional offset in T, and my offset to the beginning of this one was A1 dot log. So I add T with A1 dot log to get the final offset A dot. That's a simple computation tool. I think that's what can actually do that job. So that is, I mean, as you can see that it is actually pretty straightforward to do. So we will use this now and let us try to look at some translation. So we are looking at the example I mentioned. So here is first the declarations and the assignment statement that I'm going to translate. Now at this point, we are assuming that the declarations have been processed. So the declarations are been translated, and therefore entries in the symbol table for these declarations are happening. So let us take a look at what I expect in terms of these declarations in the symbol table. So first I would have got A. So I have the name A. Then I have the type of that. What is the type? Now, how do I get to that type is again will come in the declaration part, processing of the declaration part, which we'll discuss later. Now, what is this type? This type T1. So I've just put it as a placeholder. Otherwise, the expression was getting too wide to fit in the display. So it's of type T1, which is what? It is an array of. I'm just using a kind of a, this is called a type builder operator, which kind of gives me a type from multiple information. So let's say if we look at T2, which is the type for C5, we'll make it simpler. T2 is what? It's an array of integer of size 5. Array of integer having 5 locations. So I write that as array, that is a builder. This is the dimension, which is 5. This is a size, which is 5. And this is a type, which is 8. Element type, which is 8. So that gives me T. Similarly, so T1 is first, it's an array of array. So the innermost array is of every row, which is an array of 3 elements of integer type. So that gives me array 3 int. And this array 3 int builder now gives me a type, which is an array of 3 integer elements. So that becomes my type. I use that in the int A2 part. That is, now I have an array of such, one-dimensional 3 location arrays. So that is array 2 of array 3. So this is how my T1 will actually be. I've used some shortcuts here to show you the width and so on. For example, For T1, this if I call array3 int as T1 prime, then T1 prime will have a width which is three times the width of this type. So 3 times int dot width, which is 3 times 4, which is 12. Whereas what will be the size of? Actually, I should. I mean, this is wrong. This is little wrong in the notation. I'll correct that. I should actually write this as T1 dot width and T1 prime dot width. So what is T1 dot width? Is 2 times the size of this type, which is T1 dot width. So 2 times T1 dot width, which is 20, which is the total size of the array. So I get this size of T1. So therefore, I can put the size here as 20. Offset naturally starts it. The rest goes in a very similar manner. Actually, simpler. You have already seen that. So B will get entered next as type int size 4. Offset comes as 24 from here. Then C5 is the array C. Type T2, I have already explained, 5 int. So T2 dot width would be 20. 5 times 4, so it is 20 here. Goes in. Then IJK comes here. IJK here. 444. So up to this point, when you come to translate this expression, when you come to translating this assignment statement, at that point, your symbol table has been filled up from 0 through 5. And that information is what you will be able to. So if I'm talking about array A, then A dot array attribute would be my this entry symbol table. Similarly, my C dot array would be my this symbol table entry, from where I know the type, and from that I'll be able to compute it. So that's the basic idea. Most of the part of the symbol table gets filled up as I generate this code and keep on doing different gentem. As you know that every time you do gentem, it gets creates a temporary and gets into that. So that gentem keeps on happening. Okay, so let's now go through this. So what is the first reduction? First reduction is obviously here. K ID K gets reduced to E3. So E3 dot log becomes ID dot log K, and E3 dot type is int. How do I get it is int? Because I have got ID K, so I will do a lookup to the symbol table with ID K and find that the type. And I'll put E3 dot type as so there's a lookup involved here, which earlier not explicitly shown here, because we are just saying that as if you know ID dot type, you can maintain it as a separate attribute, or you can look up the symbol from the fact that A entry 5 which is type. So I get the first thing. Then this now has to get reduced by this production, that is A producing going back, A producing ID dot. This is my C, IDC, and this is C. And so I'll have to find out, look up the symbol table with this IDC. So I look it up, I get this entry. So A1, which is A1 dot array is ST02. That is the entry 02 of the symbol, which is array. So what is A1 dot type? A1 dot type is the type of the element. So how do I get the type of the element? I have to take the type of the array and do dereference to do component of projection on the element. T2 dot element will give me this. What is T2? T2 is array 5 int. So the element type is int. So T2 dot int, T2 dot element is int. So I got A1 dot type as int. Then I have A1 dot log, which is what I need. I'm going back is the gentem. So I need a new location to keep this index, keep this offset. So I do a gentem, I get T1. That gets entered in the location 6 of the symbol table. So T1 is the size. Sorry, T1 is what is A1 dot log. And then finally, what is the type of this T1? This is A1 dot log dot type, which will T1 generated on it. So this is T dot type. Here. So A1 dot log dot type is the type of int. Is the type of int because K was of type int, and from that it will get. So when this gets done, then I actually am going back again. Then I have to actually emit the weight. So that is E3.log times E3.log times A dot type dot weight. That is A1 dot type dot weight. E3.log is A, and A1 dot type dot weight is each dot weight, which is 4. So I can compute A times 4 goes into. So this is up to this point. I have actually reduced this whole thing. And then I have a reduction from A2. A1 is being reduced to E2. I'm going back, rule 5. Now I have to take this indexed value and take it to the temporary of. So I take that. I have to do a gen temp. So I get the location for E2 as T2. T2 dot type is obviously int. I take the indexed value, which is, let's look back. I take the indexed value now, A dot array dot base. Where did I get it? I know the type A dot array, and I paste the name of the array. So A dot array dot base is C. And I have got the index location. I'm going back again, which is A dot log. A dot log that I have got here. A dot log A1 dot log that I have got here, which is so. যাই হোক এখন ঠিক আছে sorry, possibly audio disturbances that could arise. Okay, so this becomes now the indexed location which I put to. So this finally has translated this part of the first into these two, and 2 additional entries have been made for 2 temporaries in the semantic. Now naturally the next part starts here down below, where I'm now going at ij. So now I start on this in a similar way as before. I have E5.log is I, E5.type is int, A3 array. Now this is, I have A3 as the array. So what is A3 array? Is you look up with the array index, array name. Please. So you look up the symbol table with the array name A. So as you look it up, you get 0, 0 location. So A3.array is st00. You get A3.type, which is T1.element. A3.type, this is T1.type, T1.element. Then this is wrong. This is wrong. This has to be T1 prime. Is it okay? I was hearing some noise.
Yeah, there is a little noise in the audio, but otherwise you are audible.
Okay. Sorry, so this is wrong. I'll correct that. This has to be T1 prime. This T1 dot element. So T1 is array 2 of this T1 prime. The T1 dot element will be T1 prime. Yes. So this is T1 prime, and A3 dot lock is T3. New temporary is created, and therefore exactly in the same way I get A dot lock dot type as the type of IPI, and this gets offset as well. So this is up to the reduction into A3. And then I will have reduction of ID J to E6. So E6 dot clock is J, type is int. What is A2 dot array type? What is A2 dot array type? A dot array type here is the type. What is A2 dot array? Is whatever is I'm getting from the right hand side, because it's the same entry in the symbol table. So I had A3 dot array as ST00, so I get A2 dot array as ST00. Now I have A2 dot type, which has to be again wrong here. The same error is propagating. I'm sorry. So this has to be the type already that I have got in A3 dot element, which is T1 prime dot element, which is dereferencing on this, which is T1 prime is array 3 int. So T1 prime dot element is int. So I got an element type which is int. Then I generate another location to compute this offset, which is 5, and then I get the type of that location as int, which is straightforward. So after having done that, I'm going back. Here I have to do two things. One is compute the new additional offset, and so this additional offset is in terms of T4, which is J times 4, which will be straightforward, which is this gen. And then you have T5, which is T3 plus T4, which is the two getting added here. So that is how this gets reduced to this point, where you know this is the offset. T5 is the total offset that you have got. So when you index from there by E producing A, then E4 dot log is T6, which is gen temp and put at location 11, has a type int, and you generate T6 assigned A T5, which is, what is T5? Is A2 dot log, A2 dot offset. And what is A? A is A dot array dot base. So you get that, and E4 now becomes T6. The rest of it is just completing the code. That is, you have to get the location for E1, which is T7, which is the addition of location of E2 and location of E4, that is T2 plus T6, and finally you assign T7 to 2. So this is, I'm sorry, there were quite a few typos. I'll correct those, but this is the whole process of translating arrays into in the expression in free address code. So let me stop here and ask if there is any question. Is it clear? I think this is, if you just keep in mind the address translation scheme from multi-dimensional array to one-dimensional array, the way it is laid out. The fact that C lays out as row major order, then rest of it I think is a very simple structure computation there. There doesn't seem to be any question, so let me
No.
Continue. Anything I see?
No, nothing. It's fine.
So this is how arrays will get computed on the. I have not explicitly shown an example, worked out an example here, where an array index location is being assigned a value. I will encourage you to work out that, and we will obviously have some example in the tutorial. Okay, so that was regarding the translation of array expressions. So we will now move on to how do we handle this type. And in terms of handling types for handling the declaration of arrays, I will actually take recourse to little bit more generalization and talk about some type expressions. But first, let us look into how do you handle array declarations. So I'm reproducing the declaration grammar. Do I go back? Go back. So this was the declarations. So this was our declaration grammar. So we had some left recursion here, and like this. We have the type, then the list of variables, and forming a declaration, and then having a list of declarations. So we have the same thing here, the list of variables coming from here, and then the list of declarations. But the difference is that now, instead of ID, simple ID, I could have an ID followed by indexed value showing it is an array. So earlier I had V producing v1 comma ID, now have another non-terminal C, which could either be there or it may vanish. So if it vanishes, I have rule number 9, which is epsilon. So if you put C as epsilon, then and ignore rule 8, if you put C as epsilon and ignore rule 8, then this grammar reduces to what we had last. Of course, this is the form of the grammar which use inherited attributes. Now, for having arrays, we have just appended this C. So I can have a variable which is just a simple variable, C is epsilon, or it is an array variable. So wherein we need to have ID followed by the array dimensions. So for that, I create a recursion. And I say that C produces within bracket num, which is a numerical constant, integer constant, followed by C. So this is basically the dimension value of the array. So you can keep on recurring and you will get the different dimensions. Now the question that probably would occur to you is why, more often we write recursion as left recursion. That's kind of comes natural, like we have in the left recursion. Here, why have I written this as a right recursion? There is a very specific reason of doing this. The reason I'm doing this is when you write it as left recursion, then naturally on the recursion produces a list. Any recursion of this kind will produce a list. Now, if I have a left recursion, then the exit condition of the recursion, which is V produces ID, will be the leftmost, bottommost node production. So in the bottom of reduction order, this is what we will get reduced first. And then it will keep coming up. So if you do a left recursion, then you traverse the list that you are creating by the recursion from left to right. This is the core intuition to remember. Now, in terms of an array, if I go back, for example here, if I go back, it is more important to first know about this size 3 because that is the innermost dimension. That is the simplest element that you can have, which is of type. And then you make an array of 3 elements, which becomes the element type for the next one. So, in terms of analyzing the declaration of an array, it is convenient to traverse the list not from left to right, but from right to left. So to traverse it right to left, what I'll have to do, I'll have to make a parse tree which is right rotated, where the rightmost dimension will be the bottommost one and will be the first to get reduced. And then I will slowly keep coming up the parse tree and going right to left. So I come from the innermost to the next innermost to the next innermost and finally. That is the reason that in this declaration, the grammar is written in the right recursive form. Whereas when I'm actually indexing, the particular array location, I'm writing a left recursive rule like A producing AE. I'm doing that because now I know the dimension, I know the type of every dimension. And therefore, it is easy to do a left to right traversal because I need to compute the offset from the higher dimension to the lower dimension, outer dimension to the inner dimension. Because the outer dimension takes the biggest strides, then the next dimension, then the next dimension, till you come to the innermost dimension, which takes the smallest stride. So in terms of the access expression, a traversal of the access expression, say Aij, is convenient to do from left to right. First you do for I, where you know that it has a size 12, and then you process J. Whereas in terms of declaration, it is convenient to process from right to left, where you first get to know that it is array of size 3 of type int, and then build that array, and then you know that you have an array of size 2 of array of size 3 of int. So that is the basic insight that goes in here. I felt this is very, very critical for us to understand because it's not always that you need to write the semantic rules. I mean, you can write this grammar to be syntactically correct by using a left recursion as well, but that does not make your semantic. So if we do that, then with this, something like a declaration like this should create a symbol table of this kind. A is int, B is int, X is int, Y is an array, 10 of 8, I have already explained what it means, and then we'll have a size 40, Z is int, this is array by row, size 8. I don't think this 8 is. Again, this has to be 5 times 8. Okay, so this is the basic declarations to be presented. I will stop here. I will next take a little bit of more discussion into the type expressions in general, and then talk about translation of array before moving on. So both of you, what we tend to do tomorrow in the morning class. Before I close, let me see if there are any parting questions. Any questions, friends?
Today there's a lot of issue with the audio. I don't know whether it's only at my end or not.
Any of Srijodi or Shumen are there? And they say what's happening. You had a lot of issues with the audio also?
Sir, a bit today, but later it got well. So.
It's all into. Okay. One question by Tanmay.
No, this is Tatma, I just mentioned it is a typo. I'll have to correct it. The size of array W of size 5, if I take float to be of size 8, then just to be 4. So, I mean, 4 times 5 it could be, depends on how much you take as a size of float. I think the typo I had in mind that float is of size 8, but I missed to multiply it by 5. So I'll correct. So it's been mixed, the audio problem, but quite a few have got that. Mumnath is reporting, Gaurav did not face.
Sometimes the volume is reducing by too much.
Anyway, whatever.
Not
Okay, then there doesn't seem to be any other question. So we'll continue on this tomorrow at 8 o'clock.
okay.
Bye till then. Take care and stay safe.